everybody. Hello, everybody online. Welcome. Thank you for joining us again for Science and Nature. So this is a free hybrid speaker series that we've been running with the River Institute for, I think, over 20 years. Just a bit of housekeeping for everybody online. We always love to know where you're coming from. And if you have any questions, to put in the comment section, and we'll get to those at the end of the presentation. So just before we begin, we'd like to respectfully acknowledge that we're on traditional territory of the Haudenosaunee. We offer our gratitude to the Mohawks of Akwesasne for their care for and teachings about our earth and our relations. In honoring those teachings, we are committed to the process of dismantling the ongoing legacies of settler colonialism through good relations with each other and the lands we live and work on. We're grateful for the time and knowledge that our neighbors graciously share with us, and we strive to improve the health of the Great River. I'd like to send out a big thank you to the Cornwall Public Library for offering this space for free to Science and Nature. So that has been greatly appreciated. Also a shout out and thank you to Cav Productions, who lent us the mic for this evening. So thank you, Cav. And finally, I want to give out a big shout out to all the speakers that I've had the pleasure to host for the last 4 years. It's been just such a great experience, and I've met so many incredible people. And it's the same for tonight's speakers. Actually, it's the second time that I'll be hosting them. Finally, this time they'll be in person. The first time they were virtual. So I'll be passing on this event to one of my colleagues, Lexi Harkwell, so you're going to be in really good hands, and she'll be hosting the next Science and Nature series, and which will probably be starting in January. So keep an eye out for our social media, our Facebook, our Instagram, also our YouTube. If you wanted to rewatch any of our Science and Nature events or presentations, they're there forever. You can watch them over and over again at the convenience of whenever you'd like in your homes. And so finally, we also have our annual River Symposium that's coming up at the end of October. If you have any questions about that event, you can ask Emily DeRoshi, who's just at the back of the room, and she'll be happy to answer your questions. And so finally, super excited to have Abe Schneider and Sterling Watson here today. Like I said, I had hosted them on Science and Nature previously, so 2 years ago, and so now we're kind of getting an update on their turbines and fish-friendly turbines. So super excited to hear what's new. So to give you a bit of background about Abe, he's a Chief Technology Officer and co-founder of Natel. Abe focuses heavily on the creation of hydraulic designs for Natel's turbines, and his work spans scientific R&D, project development, and communications fields. Prior to co-founding Natel Energy in 2009 with his sister Gia, Abe worked as a mechanical engineer for both large firms such as the Timken Company and innovative startups including Makani Power. Abe holds a bachelor's and master's degrees in mechanical engineering from MIT, and in his free time, he enjoys sup surfing, wing foiling, rock climbing, fly fishing, and building things with his wife and 2 children in San Francisco. So welcome, Abe. And next we have Sterling Watson, who is a principal engineer on the Natel turbine design team and focuses specifically on testing and development of Natel's turbines and fish passage studies and design tools. She has led the team's testing efforts for turbine passage of American eel, rainbow trout, and alewife, and has authored several peer-reviewed articles describing innovative methods and fish survival rates from 98 to 100%. Her passion for the natural world and all things aquatic extends into her personal life, and she can often be found on or near the water at home in Northern California. Sterling holds a bachelor's and master's degrees in mechanical engineering from MIT. So welcome, Abe and Sterling. Thank you.
Thank you, Stephanie. Thanks to the River Institute and for everyone who's joining here in person as well as online. We're super excited to be here and to share some of the work that we're doing to make turbines safer, much safer for fish. Abe and I both work at Natel Energy. We're a small company based in California, and we design hydropower turbines specifically to achieve very high rates of fish survival. So we're not a turbine manufacturer. We create designs, and we do all of our own original testing and getting the science out there to show really what is possible. And the fish that are highlighted on this cover slide are some white sturgeon. We did a big white sturgeon test this summer, and so they've been on our minds quite a lot recently. They're tiny little guys, young of year. So hydropower is a really unique and important renewable energy technology. I mean, among all of them, it has really kind of the longest legacy by many measures. And so the bar plot here shows the build out of hydropower throughout the world over the last 120 years. And you can see that as hydropower increased, we also saw a corresponding pretty significant decrease in migratory freshwater fish species. We don't actually have as long of a data set for the fish. We haven't been keeping as good of track of that, but the amount of decline that we've seen is pretty staggering, and that's not entirely due to hydropower by any means, but there are a few different ways that hydropower negatively affects these fish populations. So those include habitat loss, river fragmentation, and then also the direct injury and mortality that fish that need to migrate downstream suffer when they pass through the turbines. And so that last piece is what we focus on at Natel. And the photo that I'm showing here is one of my favorites. It's an image of one of the turbines being installed at Bonneville Dam in 1937.
Your mic's off.
Oh.
Press this button on the side.
Sorry.
It's like just on the bottom here. There we go.
Okay. Sorry to everyone online. But I was just saying that the photo on this slide shows one of the turbines being installed at Bonneville Dam in 1937. And it's kind of a fun photo. We clearly don't work in the workplace with this low level of regard to safety nowadays, but it's kind of fun to think about. And I also want to highlight just what the turbine looks like. So this is a really large turbine. If you look at the shape of the blades, and specifically the shape of the leading edge, you can see that it's very thin blade and it's moving really fast. And that's very dangerous for fish. That's also what nearly all of the turbines out there operating today look like, even though this turbine is nearly 100 years old. So we've clearly made great strides in how we regard human safety in the last 100 years, and there's quite a lot that we can do to improve how we treat fish safety as well. So why is there a problem in the first place? Sites that are really attractive for developing hydropower tend to coincide with migratory corridors for fish. And so it's this sharing of the river and flow resource that causes this problem where the flow, in order to generate the most power, we want the flow to go through the turbines, but the fish need to use that to also move around. And so we've plotted here hydropower projects throughout the US and Canada, overlaid with the migratory range of a bunch of different critical fish species. And it's important to note that basically all of these projects are currently operating with turbines that were not designed to be safe for fish in any way. So a couple of the most common turbines that are out there are the Francis turbine and the propeller or Kaplan turbine. And these turbines function based on a pressure drop across the inlet to the outlet. And when fish pass through these turbines, they may be subject to a couple of different mechanical sources of injury. So For Francis turbines, there are a lot of blades. There's a lot of opportunity for blade strike. Same thing with propeller and Kaplans, but there's an additional injury mechanism that sometimes comes up in the propeller and Kaplan turbines, which is fish getting pushed out to the outermost radius and getting caught between the moving blade and the stationary housing, which can cause a severing injury. And this is something that is particularly significant for long fish like eels. Yeah, so you can see that there, and we'll get into that a little bit more later. Another injury source that that can be significant and that we design to is barotrauma, and that's a rapid decrease of pressure that causes internal injury to the fish's swim bladder. So one of the things that makes working in hydropower pretty interesting is that every project is different. And so no matter what aspect that you're working on, fish passage being the one that we obviously focus on, there needs to be important attention to the actual specifics of the project. But something that every hydropower project has in common is that they all have turbines. So the turbine is basically the spinning heart at the center of the hydropower plant. And if designed conventionally, that poses a significant hazard to fish. So what we are working on is figuring out how can we take that piece at the core of the hydropower plant and make it much, much safer for fish if they are exposed to it. So I apologize, the data used on this slide is from the United States, but the story is pretty similar for Canada. The bubble plot shows the build out of hydro in the US over the last 120 years. And you can see that there were some pretty distinct eras of build, but in general, hydropower in the US and in Canada is very old, over 50 years old on average. And this means that there's a lot of equipment that is coming up for replacement, because the typical lifetime for these turbine parts is on the order of decades. And so there's quite a lot of old machinery, old turbines that are needing to get replaced just for mechanical reasons. And at the same time, in the US, we have a relicensing process that's going on. So this is the process that allows for environmental improvements to be enforced on these projects. And over the coming decades, next 2 decades, we're going to be seeing a huge wave of these projects coming up for relicensing. So there's a really special, this is a special point in time, because not only do we have the opportunity to take what is already out there and is causing damage and make it better, but we've got some advancements in technology that are going to make that possible. So when we thought about this problem, we decided to look at just the distribution of flow that's passing through turbines. So that's what this schematic shows. All the dots represent all of the flow that's passing through turbines in Canada. And we broke it down by 2 measures, which are the amount of flow passing through each turbine and the hydraulic head, or the elevation difference between the water at the headwater and the tailwater of the project. And what you can see is that the vast majority of projects fall into a category of less than 40 meters of head and greater than 50 cubic meters per second of flow. And actually, there's a very, very small amount of all of this flow that is less than 50 cubic meters per second. And those are projects that, by kind of the most state-of-the-art fish exclusion screening technologies, would be able to be screened. So you might be wondering, like, wouldn't it be better if fish don't pass through turbines at all? And obviously that's what the fish would prefer. But if you look at how feasible it is to actually keep fish out of turbines, there's not a whole lot out there representing, the flow that the fish are actually moving around in that is currently being demonstrated to be successfully screened. And that's just because as you get to higher flow rates, the screens get more expensive to build, to maintain, to design. And so there's been some really good work in this area. There's a few interesting publications that have come out of Europe that show kind of state-of-the-art for effectively keeping fish out of turbine intakes. This tends to be very fine screens, so spacing of 20 millimeters or less, and a very shallow incline, so 30 degrees or less. But what we see across these projects is that even at the largest scale, that's only about 45 cubic meters per second that we're able to screen. And that's also fish that are kept out by 20 millimeter bar racks. And the vast majority of fish in rivers are actually small enough to be able to pass through. So it's just not quite an adequate enough solution for all of hydropower.
So both Sterling and I are engineers, and Sterling has been breaking down the problem. So we're really trying to understand if we're going to do something to help improve fish passage through hydro, really need to know where to focus. And one is this issue of flow, and the other is driven by head. So Sterling's data showed that most of the fish passage problems are going to be happening at head less than 40 meters. And it turns out that there's a relatively straightforward way to estimate the speed at which a hydropower turbine runner rotates. And that's just a function of that head. And so when we look at the fleet, if you remember that map of North America with all those dots, so if you take all those dots at hydropower projects less than 40 meters and estimate what the peripheral speed of the turbine is, you get this histogram. So as this histogram shows, the vast majority of hydropower turbines at less than 40 meters of head have tip speeds between about 16 meters per second and up to about 40 meters per second. So the tip speed is basically the speed of the area of the runner that has the maximum radius. And that's going to be where the fish experience the worst collision if they're going to be struck by a blade. So this basically sets the speed that engineers must make safe. The way to think about this is if you're driving a car down the highway and the speed limit is 80 miles an hour or 60 miles an hour, auto manufacturers must engineer their cars so that they're safe if humans get into a car crash at that speed. And that's what we need to do in hydropower too, for fish. Unfortunately, since most of the hydropower fleet was engineered and constructed 50 years ago or more, we see that tests of existing hydropower turbines show a declining survival with speed. So this plot plots blade tip speed on the x-axis versus single passage eel survival rate on the y-axis from 60% to 100%. And you can see there's a general decline as we go towards higher and higher speeds. The eel survival rate falls from 100% at really low speeds to where you're seeing maybe 30% of the eels getting killed with one passage event. And that's sad, but it becomes catastrophic when you have more than one power plant along a river. And for low-head hydropower, it's very common to have more than one hydropower plant along a river. And eels are a species that needs to migrate upstream as very young, small fish, and then they mature to become a meter long or more up high in the headwaters and ponds, and then they need to migrate downstream as a 1 meter long fish through however many hydropower plants are in their way. And that's really hazardous, and very few eels are able to do that successfully today. So Natel's work sort of informed by all of this context that we've been sharing, but it also builds upon decades of prior work by other dedicated engineers who have been thinking about and prioritizing fish safety, or at least fish friendliness. And I wanted to highlight a couple of these significant advancements. Both of these happen to have been centered in the United States. One was an effort to create what's called a minimum gap runner. And this solves the problem of fish becoming impinged in a gap between the blades of a moving Kaplan propeller and the hub, or at the tip. So the minimum gap runner has no significant gap here at the hub, or out here at the tip. And that's a really important step forward, but this program didn't address the thickness of the blades. So if you look at the shape of the blade itself, it looks very familiar, quite thin, and it's going to be moving quite fast as well. So direct strike, especially for large fish like an eel, is still hazardous. So the Alden turbine, of which Boyth was also a key participant in its creation, was a turbine that made really big advancements in barotrauma. So in the Alden turbine, the runner is really long, and so it allows for a very gentle change in pressure through the runner. And it also had a really low number of blades and really thick blades. And pilot scale tests of this runner showed that strike still remained one of the most important causes of trauma in passage through this type of runner. And the other thing about this runner is that by its very design, it was really slow. And so that has a benefit to improve fish survival, but the problem is it's never been implemented. Because its slow speed means that it would require radical changes to existing hydropower plants. In fact, some studies showed that you would need 5 times the number of these runners to produce the same power as a conventional runner. And obviously that's just not, it's kind of a showstopper. In contrast, the minimum gap runner has been adopted in several different very important large hydropower installations because actually eliminating those gaps helped improve the efficiency of the runner in addition to solving a specific fish passage hazard. So coming out of the Alden runner development, where they sort of rediscovered the importance of strike, Alden, along with the Electric Power Research Institute, invested resources in understanding more deeply the factors affecting the survivability of different types of strikes. And the researchers in this study started using high-speed video to directly observe the interactions between fish and moving blades. And this is a really, really key concept that you'll see we've continued to build upon. The top strip of images are stills taken from 1,000 frame per second high-speed videos of a sedated rainbow trout being struck by a thin blade. And if you look at those sequential images, you can see that the body of the rainbow trout shows no real evidence of that approaching blade until physical contact happens. And then there's kind of a violent change in the fish shape as it bends around the leading edge. And at 7 meter per second strikes, 50% of these fish die due to spinal fracture. But in contrast, at roughly the same strike speed, a trout struck by a blade which is as thick as the trout is long, almost 100% of those fish survive. And if we look at the strip of stills taken from the high-speed video, we can see something really interesting happening. So the body of the fish is actually starting to adopt the shape of the leading edge of the blade, even though there's no contact with the blade. And that's evidence of something mysterious happening in the fluid. It's actually, there's a high pressure zone that's in front of any object moving through a fluid. But in the case of blades having these large proportions relative to the fish that they're striking, that high pressure zone is large enough to actually work on the fish. It actually is like a cushion that causes the fish to start deforming in advance of a strike. And in our subsequent work, we've been able to show that many fish never even would contact the blade because that high pressure zone actually pushes them out of the way. And if anyone's driven a pickup truck with a bug deflector on the front, it's not quite the same thing, but it's similar. You're using fluid dynamics to reduce the likelihood of an actual strike and to reduce the severity of the strike if the strike actually happens. So this was great, and it showed basically the ability to take what used to be a 50% mortal strike to nearly 100%. And as engineers, that's great information. Unfortunately, 7 meters per second is roughly half of the speed that we actually need to be designing for. If you recall that histogram of tip speeds, 7 meters per second is nowhere close to the actual strike speed of real world hydropower turbines in the fleet. So something else needs to be done to further improve the strike speeds at which fish can survive. And this is where Natel's contribution comes in. Our basic idea was, what can we do to maximize the safe strike speed of hydropower turbine blades? And our simple concept is kind of sketched out with this this cartoon here in the lower left. And the idea is that a normal hydropower turbine blade, in a normal hydropower turbine, the blades just emerge radially from the hub, because that's the simplest and most structurally efficient thing to do. And when a fish is struck that way, it's kind of receiving the full impact. It's experiencing the 100% of the relative velocity at the point of strike. But what if we could change the shape of the leading edge where fish are struck so that they're hitting a sloped surface? Then theoretically, the force felt by the fish will shrink as a proportion of that, as a sine of that angle. And it works, turns out, if you remember your trigonometry, that sine of 30 degrees is 1/2. And so we could roughly double the safe strike speed if we simply sloped the blade by 30 degrees. And so that's actually what results in these unique looking blades on the right-hand side of the slide. These are sort of characteristic shapes that Natel has created, which have a 30-degree slope or thereabouts out at the tip where the blade's moving the fastest. And then the blade sort of arcs down to a 90-degree slope at the hub where the blade is moving slowest. And so this is a way to engineer the leading edge of a blade to sort of maximize the strike survival while still resulting in a blade that can be manufactured. And so the key thing is that we start with the requirements for fish physiology. That drives the leading edge shape. And then everything else about the hydropower turbine blade is evolved from that. So manufacturability and hydraulic efficiency, cavitation resistance, all of those things basically drive the selection of the thickness profiles of the blade. But what comes first is fish safety, because you don't accidentally arrive at turbine blades that look like this if you're only prioritizing hydraulic efficiency. So we tested this thesis in the laboratory at Alden back in 2019, and we published a peer-reviewed article in 2020 that basically substantiated this hypothesis, and we saw an increase in strike survival from around 25% with a 90-degree leading edge slope up to 100% at 30 degrees at the same strike speed. And everything that we've done since that point in 2020 has been to reduce this to practice, to create real turbines and to conduct a whole slew of fish passage tests with different species and under different conditions, and then ultimately to scale this technology up. And that's what we'll discuss next.
Yeah, so Abe walked through the theory, and that's pretty much where we got to in 2019. But ever since then, we've been really focused on looking at how this actually works in practice. So this is a pretty unique facility. What you're looking at is an overhead view of our hydraulic testing and fish testing lab. So this is a recirculating piped loop. We have a pump that sends flow to the turbine located over here, and we can operate this in a very controlled way across a range of operating conditions. We also have our own recirculating aquatic system, which allows us to hold fish for as long as we would like. And so having these two things together allows us to, on demand, collect really useful data about different fish species passage through the turbines. The way that works is we take fish and we put them into the injector located upstream of the turbine. That's basically a pressure canister that we then raise to the pressure of the pipeline. And then we open a valve and the fish are sent into the pipe. The flow is moving really fast. They move downstream. They pass through the turbine located here, which is equipped with a transparent runner housing. So we're able to observe how the fish actually pass through and interact with the blades when they pass through the turbine. And then from there, they move downstream, they're extracted from the flow, and they reappear in the fish recovery tank. And a typical amount of time between when we see fish move through the injector and then reappear in the tank is 8 to 10 seconds. So we're able to get a really immediate look at how the fish are doing when they come out of the turbine, and also pair those observations with what the fish actually experienced when it passed through. And so this is a sampling of what that video looks like, and also the survival rates that we've seen. We've got a lot of information on our website, including some additional species that we've worked with. But see, these are some of the studies that we're kind of most proud of, I guess. The American eel study we performed with the Pacific Northwest National Lab in 2021. That work is published in Transactions of the American Fisheries Society. And that study was designed to look at a pretty extreme case. I didn't mention on the last slide, but that test turbine is 55 centimeters in diameter. So that's really small. And it's small because that's what our pump can supply. And it allows us to have this very special transparent housing. But it means that we have to test with relatively small fish to represent what's actually happening in full-scale turbines, which can easily be 10 times bigger than that. But for this test, we worked with relatively large eel. So some of the eel were actually longer than the diameter of the turbine, and every single eel in that study contacted at least one blade. So that was useful because we got to see what happens when the eels contact these specially shaped blades, and we saw 100% survival as a result of that work. The example in the middle is a study of juvenile alewife or Gaspereau passage through one of our turbines in the field. This was actually the first turbine we ever built. It's the same size, 55 centimeters in diameter. And we were able to build this special transparent half-runner housing and bring it to the field site to actually observe what was happening to the fish as they passed through. And like Abe mentioned, hopefully you can see it here, but there are a lot of fish passing through the runner in different locations, different orientations, but they're not actually colliding with the blade and moving with the velocity of the blade, which is what we would consider a severe strike from what we've seen in our laboratory studies. The fish are basically getting pushed out of the way of the leading edge. And that is in agreement with the survival rates that we saw, which were 100% after a 48-hour hold period. And then finally, like I mentioned on the very first slide, we just concluded our largest study yet with juvenile white sturgeon. We did this study in collaboration with University of California, Davis. And we studied a bunch of different things, sublethal effects of passage, not just the direct survival rate. And that data is too early to share, but I can say that we saw over 99% survival across the entire study. And Abe also mentioned that many fish, including eel, need to pass through multiple turbines in order to actually make it to the ocean. This is something that we have gotten to study a little bit. We got to study it, the effect of repeat passage in the sturgeon work. We also did it with the eel, which is what you're seeing here. And so this is the same eel in the photos and the videos on this slide, showing its condition prior to passage through the turbine and then after each successive passage. And for this study, we again saw 100% survival. So it's obviously what we're targeting. So we've put quite a lot of work into developing the science, collecting the data, developing the theory. But the next step is, how do we implement this? And one of the very important things that we need to do is make people aware of what is possible. That's why we're here today, and why we're so glad to have you all here. So Abe will talk through some of our process for looking at projects and looking at how we can implement this technology.
One of the most important things to realize is that this advancement that we're describing is an advancement in design. It's not a turbine with a capital T. We can create turbines that look very different holistically from each other, but all share very similar attributes for strike survival, for example. So they'll have very similar looking leading edges, but the resulting turbines some might be vertical, some might be horizontal, and so they end up looking quite different. But that's the most important thing to realize, is that this is a way to design turbines, and especially to design modernization of existing turbines. And that's why we have this picture here. So this is taken inside of a power plant on the East Coast in the United States. And you can see that the shaft of the turbine is horizontal. So this is what's called an S turbine. It's a Kaplan turbine, meaning that the blades of the runner can pivot. So it maintains high efficiency over a wide range of flow. And this is representative of a lot of the low head hydropower fleet on the East Coast. And I would just like to walk you through some of the practical steps of how do we get from an old plant that might need to be re-runnered to a design for a runner that fits the constraints of that existing plant and produces the same power at the same efficiency as a conventional runner design would be, but passes 98 to 100% of fish instead of passing 70% of the fish safely. And does so without any special operational requirements. The plant operator can keep running the turbine just like they normally would. So in situations like this, which is by far the thing that we are doing the most nowadays, is designing new runners that are fish safe for existing hydropower facilities. So in that case, what we'll do is we'll work with the plant owner to digitize their plant. So that means taking sometimes 100-year-old drawings of their power plant and then creating a modern 3-dimensional CAD model of, of the water passageway. And then we use that to create a new runner that fits within the constraints of that water passageway. One of the most important things to making feasible fish-safe designs is understanding how to keep costs low. And so a lot of times we're under tight constraints to reuse as much as possible of the existing civil works and to reuse the existing generator, for example. Those are the most expensive aspects of an existing plant, and try to just keep the changes to the minimum. So we create this CAD model. We use the CAD model to start iteratively generating a runner geometry. Then we mesh that, so we make a computational mesh, and we use that to make a computational simulation of the flow. And so these pretty colorful pictures are effectively, they're showing you the distribution of velocity through the water as it's flowing from the inlet to the outlet of that turbine. And then the two images of the runner itself, the reddish looking one and the bluish looking one, those are views from upstream and from downstream respectively, showing the static pressure that's on the blades of the runner. And so these are all outputs that are very, very conventional. Every normal hydropower turbine designer knows how to use these techniques. They're state-of-the-art techniques. And they're essential for us to create a runner that's both simultaneously high performance conventionally, but also a safer fish. We then make sure that the runner can be built and manufactured and it won't break. So we go through finite element analysis and normal structural design techniques. But then probably most importantly, from the standpoint of fish, we've created computational processes to be very specific about how fish safe this really is. And that's this top right image. And Sterling will talk a little bit more in detail about what exactly goes in there.
Yeah, so this is a look under the hood at how we simulate fish passage through our turbine designs. We use CFD, computational fluid dynamics tools, to create our turbine designs just like every other turbine designer. But in addition to optimizing for conventional metrics like efficiency, power, and flow, we also can optimize for a target fish survival rate. And so what we do is we take a solved flow field and we release these representative fish particles into it. Those particles pass through the flow, and then we're able to pull information from the trajectories that they take through the turbine and correlate those to actual survival data that we've collected experimentally. So on this slide, there are simulations of 2 actual tests that we conducted on our test stand with channel catfish last year. The one on top was performed with a runner that has 3 blades, and it spun at a rotation rate of 667 RPM. And then the one below was performed later in the year with a different runner that has 2 blades and spins almost 50% faster. And so these were entirely different tests, but what we did is we took the actual size distribution of fish from the experiment and we represented that with an appropriate normal distribution in CFD. And then we compared the model predicted survival rate to the actual survival rate that we observed. And you can see that those numbers come really close. So that's something that's really important for us to be able to confidently design for a specific survival rate for a fish of a given size. And this, that same data is also represented on this plot here. And so what we've done is we've tested across a wide variety of species, and then we've looked at how well does our model predict the actual survival rate that we saw for all those different conditions. The teal bars are the experimentally observed mortality, And the orange bars are the model predicted mortality from our CFD-based fish particle model. And you can see that there's a really good agreement across a wide variety of these conditions. And so that's basically why we put so much effort into creating these tools. Because if you look at the yellow bars and the gray bars, those actually represent much simple spreadsheet calculation-based models that are more typically used by the industry, and those can provide somewhat valuable insights, but you can see here that they're not doing a very good job of predicting the actual survival rates that we see. So this is just another important point to show kind of like the development that needs to be done and that we've been working on to have confidence in being able to truly design for very high rates of fish survival.
Okay, so where do we go from here? We've shown you a bunch of our work with 55 centimeter runner diameters, but we've also made the point that the most important problem to be solving in hydropower is to solve problems with large turbines with greater than 50 cubic meter per second per unit. And Natel is very actively working in the design of multiple large machines now. And this is a good example of one where this is a turbine that Natel was invited to design for a power plant that has multiple units. It's a 100 megawatt class hydropower facility. You can tell from the scale of the person next to the turbine how large this is. It's over 4 meters in diameter, and the runner produces over 26 megawatts of power from one runner. The existing runners at the hydropower plant where this is intended to go are estimated to be killing about 30% of the eels that pass through that plant. Natel was able to create a design that brings that survival rate to over 98% under all operating conditions. But even more importantly, this is a runner that can mechanically bolt in to replace the existing runner, reusing every other aspect of the power plant. So no construction and no change to the electrical machine. And this is at a plant where the existing runners are over 50 years old and are already suffering outages and forced replacements or forced modernizations. So this is an opportunity for the plant owner to make a big leap forward in environmental sustainability while preserving their power generating capacity in the simplest possible way. It's also an example of our role in this whole workflow in the community as a turbine designer. The manufacturer of the turbine is a well-known, well-established turbine manufacturer with many, many decades of history and dozens of references of already installed turbines, both above and below this size. And sticking to this theme and sort of helping to illustrate the point that this is a design approach that's quite flexible and can result in turbines of a surprisingly diverse, set of physical appearances. These are 3 different examples of turbines that Natel is actively designing for large utility customers. On the left is a vertical 7 megawatt Kaplan runner. So this is a Natel style leading edge that is fully adjustable. So instead of the blades being fixed, these blades can pivot. And so this turbine can maintain over 90% efficiency down to 40% of flow or less, and reaches a peak efficiency of over 93%. The middle example is the same example that I just showed in highlight on the prior slide. But the right-hand example is an interesting one. We're able to apply these same design techniques to not just axial flow turbines like propeller and Kaplan turbines, but also to Francis turbines. And this is important for migratory species like shad, where Francis turbines are notoriously dangerous to adult shad. So one of the things that Natel has done with our partner, the University of California, Davis, under a US Department of Energy funded study, is to conduct the first of its kind apples to apples comparison tests between a Natel style FishSafe runner and a runner designed with textbook conventional principles. So this is something that hasn't been done before, but the data now exists to allow for direct observation of how fish pass through a conventionally designed runner and some of the hazards that they face. On the left is a white sturgeon passing through, and the circle kind of highlights its passage, and you can see that the sturgeon is bumped, and over 99% of these fish survive. On the right is the poorly understood hot dog fish. But the physical dynamics that you see happen to that hot dog are nearly identical to what we see when fish of multiple other species are passed through. So at this time, we have this same type of information for sturgeon, eel, as well as trout. And the results are quite stark. And they basically, I think the important thing to understand from these two side-by-side videos is that these are turbines that are hydraulically similar. So they're rotating at the same speed. They're producing the same shaft power under the same head with the same flow rate, operating in the exact same turbine. So that same wicket gates, the same draft tube, literally everything about the piping is identical. And the only thing that's different is the shape of the runner. And I think this very clearly makes the point that there is a better way to design runners if you prioritize the safety of aquatic organisms alongside power production. And we know how to do it today. Taking a drier look at the data, this is that same plot that we showed a few slides ago, overlaid with two of the results from eel passage tests that Natel has conducted. And this is extremely promising because what we're starting to see is that it's actually possible to design hydropower turbines in the speed range that matters to the commercial fleet today. So, that 16 to 35 plus meter per second range of speeds, we are putting points on the scoreboard that show above 99% survival at those speeds. And this is very promising for the future of hydropower, conventional hydropower, to continue operating, but with safe fish passage through the turbines.
So I wanted to conclude with a couple of thought-provoking anecdotes. I mentioned the very first turbine that we installed. We performed the juvenile alewife study. This was back in 2021 at a project in Maine. It was a very small project, and in the course of setting up our equipment to recapture all the fish at the outlet, we incidentally captured a whole lot of other fish that just happened to be passing through the turbine all the time. And so you can see that we captured very small freshwater mussel. We captured black bass, many crawfish, all of them with their claws intact, as well as suckers and sunfish of various sizes, and even a relatively large eel that happened to pass through the very fine screen that was present at that project. And so this was super exciting for us because it's fun to get a look at what's actually in there. But it's also a really important reminder that these fish are moving through our turbines all the time, and we're able to pass them safely, like we saw here. So some concluding thoughts. Real significant improvements in turbine passage are happening now. There's been, like Abe said, a long history of fish-friendly turbine development, but we believe that we're putting out information that shows that we can do a lot more than what we were able to do in the past. Also, turbines are a critical part of the fish protection toolkit, just like all other aspects of fish passage. They're important because every hydropower project has a turbine. And so this final look at some of the alewives that we used in our study just kind of shows how can we all kind of swim in the same direction, work together to take advantage of the opportunity that we have right now to take our existing fleet and make it better for fish. So thank you very much. I think we have time for questions.
Take your mic, and I'll use it for the questions. And then you guys could share that one.
Yeah, check that I didn't just turn it off.
No, it's good. Okay. Oh, thank you.
Okay, are there any questions in the room? Oh, okay, here, we'll start here.
I wanted to ask that the flow is going downstream, so you tested going down. Are there fish that can go up and against it?
Yeah, so that's a good question. The velocities through the turbines are really high. So we're not able to use the same passage route for fish to go upstream. We still will need fish ladders, eel ladders, things like that to get the fish upstream. But and that's a difficult problem. That's a problem that a lot of people are working on. But the problem of actually directing fish away from the turbines going downstream is one that when we started working in this space really didn't have very compelling solutions. So that's what we're focusing on specifically.
Thank you for that talk. It's very inspiring work. I had a question, an engineering question, I guess, about if the fish-friendly blades are striking things less, would that translate to a longer lifespan for them? You know, there's less impacts, less damage to them potentially as well that you could market.
Yeah, we've conducted studies with a laboratory in Europe which specializes in abrasive erosion studies and found that blades having these fish-safe shapes experience 5 times less abrasive erosion compared to a normal shape. And also, so that's just the abrasive erosion. But another nuisance is if leaves or trash bags or stringy debris, come downstream, they can hang up and foul your turbine. These blades are so generously proportioned that stuff just doesn't hang up on them. They just like wash by. So yeah, I think it actually significantly reduces some of those normal headaches of owning and operating a hydropower facility. They're very, very robust and strong pieces of machinery in addition to being safe for fish.
Hi, thank you for your presentation. The parts that weren't over my head were very interesting. A few years ago, I worked on a project with an academic on metal fatigue, specifically in Hydro-Quebec turbines. The issue, as you've mentioned, it's aging infrastructure, blah, blah, blah. But the issue specifically for Hydro-Quebec is that in order to maintain the turbines that have metal corrosion, they have to shut the whole thing down. And that's downtime and lost productivity, lost profit, et cetera, et cetera. So my question is, are you considering other factors such as advanced materials, which is what this project was about, in your design of new turbines and rotors so that Hydro-Quebec does not have to choose between lost profits and fish, because I'm pretty sure I know which one they're going to pick.
Mm-hmm. Well, our very first turbine of above a meter diameter that we built was a composite runner. So it used some of the most advanced material techniques, totally corrosion resistant. It's impossible for it to corrode. We think that the majority of utility owners will not prefer to go that far down. They'll tend to actually require use of the same alloys that have been used reliably in runner creation. So I think that will tend to force the continued use of certain metal alloys. But it's that the shape of these blades does lend themselves to the use of composite construction if that were to become more favored by the owners. So it's absolutely something that could be done, but it doesn't have to be done. So if the time comes where that's prioritized, then we're ready to go there. Basically, there's a range of materials and manufacturing techniques that can be used. And we've already demonstrated them. In fact, we have a roughly 2 meter diameter turbine that has carbon fiber blades. That's, I think, possibly the longest running, largest composite runner in the world. I don't know. Wasn't really the point of that project, but a lot of our engineers on our team have aerospace backgrounds, and so we're familiar with designing with those materials and techniques. But we have found that there's basically more interest in the conventional metals, at least in our experience. Sounds like maybe your client would be open to thinking of other techniques too.
They were looking at different high tensile steels.
Okay, yeah.
We also have a question coming in from online from Tom. So Tom is asking, do state-of-the-art turbines make fish ladders redundant?
Yeah, I think that was a similar question to the question in the physical audience, and the answer is no. So downstream fish passage is, one has to think about the two. You have to think about downstream fish passage and upstream fish passage when you think about the health of the watershed. But a solution for downstream fish passage is does not alleviate the pressure for a sufficient upstream passage. And also effective upstream fish passage does not, in most cases, solve downstream fish passage.
Yeah, so a clarifying point there is that fish will not use ladders typically to go downstream, and fish are not able to use turbines to go upstream.
Oh, I thought you were going to run. Okay, thanks. So I have a question here. Sterling, in your introduction of the part explaining, the impacts of turbines, you talked about the importance not only of blade strikes, but of things like barotrauma. So I might have missed is how, what I understand is, especially from the videos, it shows the differences in terms of blade strikes or the way it is, but how is barotrauma reduced by these blades? And then I have a second part to the question.
Okay, yeah, that's a really good question. And barotrauma is something that we've been really heavily focusing on recently. It can be the most significant driver of fish mortality that we're predicting for specific projects that we work on. And the simple answer is there's nothing about these turbine blades that make them safer for barotrauma. The thing that can make our design safer for barotrauma is paying attention to it. And so understanding, basically barotrauma occurs when fish are exposed to very low pressure regions. And so understanding how frequently they're going to encounter those regions, quantifying that in CFD, allows us to tweak the shapes of the blades to really minimize that exposure. It's also a function of operating point. So when turbines are operated at max flow, they're opened all the way up, then you get higher velocities, and higher velocity means lower pressure. So if we're looking at the way a project currently operates, we can understand during which parts of the operating season there's going to be more risk of barotrauma versus less. But in general, barotrauma is something that I think is not studied quite well enough, and so it's something that we continue to seek new information on to just give us more confidence in designing for that as well, because it is really important.
Yeah, interesting. Thank you. And the second part of the question, or sort of the other thought that came to me, so in ecotoxicology, I'm an ecotoxicologist, we talk about short-term effects and long-term effects. Short-term effects are 48-hour tests. Long or chronic tests are longer than that. So your survival rates are 48-hour survival rates. Have you looked at effects that may not be visible after 48 hours, but maybe occur longer term? So I know that's sort of, you're trying to take care of the big part first, but I'm just wondering if that's a further sophistication on your testing.
Yes, it is. Okay, Abe just took us to this slide. So this was kind of one of the first things we did to poke at that question, which was looking at how the fish fare if they pass through the turbine multiple times. And one thing we saw was that incidences of minor injuries were not more frequent for eels that already experienced them previously. So that's one thing we learned early on. But I will say that our most recent work this summer with white sturgeon was really focused on looking at those sublethal effects. Our team, we're actually a bunch of engineers. So we, on our team, have developed some very pertinent skills, but we needed to partner with experts outside of the company, with fish biologists from UC Davis, to develop a study that allowed us to look at some of those sublethal effects. And so specifically what we studied was the effect of turbine passage on growth rate. So looking at fish that were kept at the lab, fish that were exposed to a control treatment, so exposed to all the handling, anesthesia, et cetera, but not passed through the turbine, and then fish that were passed through the turbine. We also looked at the effect of turbine passage on behavior. And then we also looked, the biggest contingent of fish in that study was ones that we were sampling for blood stress hormone levels over time. And
Excellent.
that data is not out yet.
Excellent.
But we're working on it.
It will be published.
Yeah.
Do you have any indication that the regulators, as all of these dams come up for relicensing, are likely to make these fish-friendly turbines a requirement of the relicensing process?
So that's a really good question. We think it should be. We think that there's no good reason for turbines that are not safe for fish to be installed now. But I think that what we've seen is we've really only been doing this for a little over 5 years. It's a really new technology, and anyone who's been knowledgeable about fish passage and hydropower for a long time has a lot of reason to be skeptical of the actual experience and survival rates that fish can have in passing through turbines. And so that's something that we've really focused on studying for ourselves and getting the information out to understand both at what point are the speeds too fast, or the fish are too big, or the blades are too thin, to actually achieve survival rates, so we can define those thresholds and then remain within them. And I think that what we're seeing in working closely with regulators and experts and academics in creating our designs and getting the information out there is that they're recognizing that this is a really important tool.
Thank you. Oh, here.
How are the production costs of the different design comparable to conventional?
Yeah, the question is, are the production costs comparable? And I think the short answer is yes, they're comparable. In many cases, there will be the same or one fewer or a small proportion fewer number of blades, which tends to offset an increase in material due to the increased thickness. Also, for large utility runners, they'll be produced hollow, so they consume quite a bit less material than you might imagine. And that's also important in order to make reuse of the other existing mechanical portions of the turbine as well. And a lot of times, even if there are, say, noticeable percentage differences in the runner cost itself, that cost is a small fraction of the actual overall modernization cost, which includes the outage itself and all of the complex project of disassembling and then reassembling the turbine and recommissioning it.
Locally, the dam of interest, of course, is the Moses Saunders Dam, which is, 65 years old now. And obviously, hydraulics have changed over the years because Ontario Hydro did change the 16 impellers on our side about 10 years ago, and I understand they've improved the electrical production capacity by about 5% just from changing the hydraulics. I don't know whether they did anything for fish passage or anything. Maybe you know, I don't know. I don't think the turbines on the American side have been changed yet. So there may be an opportunity there. However, and slide 26, I think it was, showed that the mortality rate is in the order of, or S there now over at the right-hand side, halfway down there, about 75% survival rate or something, or 26% mortality. I don't know whether that's improved or not with the impeller design change. Do you know that? However, my question is, this is not the only problem with the fish going through the turbine. There's a reduction in barometric pressure or whatever you want on the fish itself. It's swimming around at 30 meters deep or something other. Within 10 seconds, it's sitting on the surface at 0 meters deep. Do you know, or have you studied what happens to the swim bladders of these fish? And like I imagine that many of them just blow up and the poor fish blows apart. Is that true, or what do you know about this subject? It's outside of your hydraulic study, I know that, because your test equipment there is going from 0 pressure to 0 pressure, really, and not looking at that.
Yeah, okay. So there's a few things in your question there. I don't know whether the survival rate that you see here is representative of what's there today. In general, there's a lot of gray literature in hydropower, and so we would love to see that information and really understand it fully. But the data that's plotted here is specifically for eel, and from what we know from laboratory studies of barotrauma rapid decompression for eel is that they are kind of surprisingly unsusceptible to it, and that may be an artifact of the testing. The eel are a benthic species, and so they tend to have less air in their swim bladder so they can stay negatively buoyant. That's a helpful thing when it comes to barotrauma, because if they have more air in their swim bladder, when they're exposed to a lower pressure, that air is going to expand more and cause injuries like swim bladder rupture. So that's what we know about eel. We have done a bit of our own barotrauma testing with a variety of other species, especially species that don't have their swim bladder connected to the mouth. So these are fish that basically cannot release any expanding gas. They're going to have a rupture if they're decompressed quickly. And one of the things that we came across when we started working on this problem was just a general understanding that for low head projects, barotrauma wasn't an issue. That was just kind of what people said. And what we found is that you can actually have barotrauma at low head projects, especially if they are operated consuming really high flow rates. If they're positioned elevated above tailwater, that can make a really big difference, because the higher up you position the turbine, the more suction there is. And so just decreases the pressure through the whole volume. And so I don't know if that helps to answer your question, but these are real problems that we see. And without knowing more about the specifics of any particular project, we can't really comment on what that would be. But if we are working on a design for a project, then we, like Abe said, we can recreate the whole water passageway, and we can study both the strike risk as well as the barotrauma risk.
So my question was really enough to say this 26% mortality rate at the moment, change the impeller to do all the hydraulics and that, will we still say have 24% mortality just because of the pressure drop across the from up the upper level to the lower level? And
so we wouldn't expect that for eel.
Well, eels don't have that connection to the mouth, right? I mean,
they do.
No, I don't think so. Don't they generate the air inside them? I mean, they take several hours to go from, a few hundred feet down in the ocean up to the surface and back and so forth. But that's a lot different than 10 seconds across a dam.
We haven't studied barotrauma in eels specifically. The laboratory studies that I mentioned were performed by scientists at Pacific Northwest National Lab, and they did have a hard time getting the fish to acclimate to a given pressure because they basically just stayed neutrally buoyant. So it's possible that there's more barotrauma susceptibility than they revealed in those studies, but from what we know, we don't anticipate them to be particularly susceptible. But in every project, we're going to be looking at every species of fish that's going to be passing through the turbine. So if they're eel and shad, or eel and salmon, then we do have better data on the barotrauma susceptibility for those species, and we would be designing for that as well.
I just wanted to add a comment related to the performance note. So we know that it's possible to design FishSafe turbines with efficiencies over 94%. We already have multiple examples of that. So in a situation where the goals of a station rerunnering or modernization are first and foremost to improve energy output, that does not have to be incompatible with also gigantic improvements in fish passage safety.
So we have another 2 questions coming in from online. So Zane is asking, would it be relevant to consider passage through Kaplan turbines in pumping mode?
In what?
In Kaplan turbines in pumping mode.
Yes.
Okay, awesome. Question number 2 is from Pierre Marc, who said, did you study injuries caused by cavitation? Can it be considered as an important factor as a blaze strike, or is it considered a minor factor?
Typically, cavitation is something you don't want anyway. So we're spending a very large amount of effort driving the risk of cavitation out of the turbine. Cavitation will cause effectively severe baro trauma. So it's not something to be trivialized, but also, especially if you're designing a new runner, we are going to be spending a large, probably the largest amount of effort in the design project will be focused around achieving really uniform and non-cavitating pressure regimes.
Great. Yeah, we haven't specifically tested. We haven't specifically passed fish through a cavitating turbine. I don't think anyone has, to my knowledge, has done that. We would anticipate it would probably not go well for the fish.
Yeah, I mean, the blade would be damaged, right?
Yeah.
You hit the blade and very quickly have to replace it.
Something for curiosity's interest. If you read our eel paper with PNNL, we note that we observed fish body induced cavitation. So the fish, when it passes through the runner and say it gets hung up on the leading edge of the runner, can create a local disturbance in the water passageway. And we observed cavitation on the fish body in those instances and videoed it. And we did not actually see that resulted in a detectable, certainly no mortality, and we couldn't detect a trauma from it, actually. It's kind of interesting.
Excellent. Thank you for all the questions. You could hang around and, if you have more questions that you want to ask Abe and Sterling, you can hang around as we, take things down. But thanks again for joining us for Science and Nature. Thank you for your support, and keep watching our social media to see what comes in the new year with Lexi Harquell. So thanks again, and thank you for coming.